Welcome back. I hope you enjoyed your lunch. Now is talking John Spray, and he will talk about Ceph.
Thank you. So today's talk is going to be a deep introduction to Ceph, followed by an update on the latest development in the recently released Hammer version. So I'm going to talk about what Ceph is, for those who don't know, how it works, how it stores your data to guarantee resilience and redundancy, how your applications can talk to Ceph, and then finally what's new. Before I go any further, quick show of hands. Who already knows what Ceph is? Good, most people. Who is already using Ceph? Okay, good number of people. So this will be interesting for at least some of you, but a few of you can correct me if I'm wrong. So Ceph is a highly available data store. It's free software. It's LGPL and it's all LGPL. There are no proprietary add-ons. It's a comparatively old project. It's been going for 10 years. It was originally started by SageWhile as a high-performance computing file system, but it's become a lot more versatile than that since then. It's available for use as a block device, as an S3-compatible object store, or as a file system. And the place that you see it most today is in private clouds, where people either need a store for their virtual machine images or an S3-compatible object store for their application workloads. More generally, Ceph is what I think most people want in a storage system. It's a piece of software where you feed disks in at one end, and you get usable storage out the other end. It makes sure you don't lose your data. It doesn't require babysitting to do that. And you can run it on more or less any Linux platform you want. It's portable, and occasionally it's been run on non-Linux platforms as well. Object storage is provided by the Rados gateway, which is shortened RGW on the left-hand side of this slide. So that's compatible with S3, that's how most people use it, but you can also use a Swift-compatible interface there if that's what your applications want. It supports geo-replication, so you can have a master and slave data center or region to ensure you have multiple copies of your data as well. The block storage, or the virtual disk, is provided by the Rados block device, or RBD, that's in the middle. And it's a fairly advanced network block device implementation that includes snapshots, copy-on-write clones, and that kind of thing. And finally, the file system on the right-hand side is a POSIX-compatible shared file system, similar to an NFS filer, but a lot more scalable than the average one. So now I want to talk about how that all works. So those are the three components again in a slightly different form. And in this diagram, there's the layer along the bottom as well, which is Rados. And that's the underlying object storage platform that supports all of the different application interfaces. So whether you're using RGW, RBD, or the Sef File System, your data is ultimately being stored by Rados. Rados stands for Reliable Autonomous Distributed Object Store. It's reliable because it will keep more than one copy of your data and make sure that those copies are maintained in the case of failures. It's autonomous because it doesn't require administrator interaction to do that process. It will notice failures and fix them itself. It's distributed in that it scales linearly. You can use it on anything from tens to tens of thousands of drives. And of course, it's an object store. A Rados cluster consists of two types of service, usually running on separate servers. OSDs, which are object storage daemons, and monitors. So OSDs are essentially your disks, and their job is to serve data to clients, to receive reads and to service writes as well. They talk to each other as well as clients. So all of that replication and self-healing happens on a peer-to-peer basis between OSDs. Monitors, you usually have 3 of them, perhaps 5. You need an odd number of them because they form a quorum using the Paxos protocol. And they maintain the most important state of your system. They tell the system which OSDs are available, which are up, which are down, and take care of managing that. So object storage daemons themselves are C++ applications that sit on top of a disk. But between the OSD service and the disk is usually a local file system. By default, that's XFS. It can also be something else. You can use a file system of your choice. Btrfs is quite interesting for some people because of its copy-on-write snapshot capability, although it has the stability issues that Btrfs generally does, so most people are using XFS in production. In the most recent versions of Ceph, it's also possible to use experimental non-file system backends at that layer. So you may have heard of LevelDB or RocksDB. Some of these emerging key value stores get very good performance out of solid-state devices, and so Ceph supports using those as well in an experimental capacity. From the application's point of view, it sees all of those OSDs and monitors in a big group, and it addresses them collectively. So applications don't think about, I'm going to talk to this OSD or I'm going to talk to this monitor. They address the cluster as a whole. And all of the mechanisms for deciding which server to talk to are hidden inside Ceph. Applications initially only need to know the address of a monitor to learn about the addresses of all the rest of the cluster. So within that cluster, the most important decision we have to make is where to put the data. There are a variety of ways of doing that. The most traditional one is to have a metadata server that would tell you for a given file or S3 object or disk image what server it should be stored on. The problem with having a metadata server is it quickly becomes a bottleneck. If you have a very large number of servers and a single metadata server, then your linear scalability is limited by your metadata. It also adds latency because you have to do 2 lookups for everything that you want to find. Preferable to a metadata server is to do some kind of calculated placement. So the most simple example of this, and this is what some systems do, is to take the ID of a file or a disk image or so on and hash it and look at the low few bits of the hash, or if we imagine it as an alphabet, the first letter, and use that to decide where in a range of servers the data should be placed. That works quite well for certain simple use cases. Where it doesn't work so well is when you need to pick multiple locations for data, because you need a smart way of doing that. You don't necessarily want to put things on 2 disks in the same server, or conversely, if you have a performance requirement, you don't necessarily want to put them on opposite ends of the data center. And it also doesn't necessarily cope well when you add and remove systems, and you have to move these boundaries between areas of the hash space. So in Ceph, there's an algorithm called crush. And this is the algorithm which allows us to quickly decide for a given piece of data where it should live, and more importantly, on which multiple servers should it live. The qualities that an algorithm should have to perform this purpose are that it should have a repeatable distribution. We need to make sure that when we run the calculation again, we'll find it the same place we put it. Also to have a stable mapping. So if we add or remove drives, we won't shuffle a lot of data back and forth. We'll move more or less the minimal amount of data we have to adapt to drives coming and going. And it should also be topology aware. So the placement algorithm needs to be making intelligent decisions about whether to put copies of data in different racks, in different hosts, rather than just putting them on different disks. So visually, this is the job that's being done by Crush. Some data comes in. It's split up into multiple objects at the RADOS layer. So these become RADOS objects and the different colored blocks. On the right-hand side, you can see the different OSDs, the squares. And each block, in this example, is going to 2 different OSDs. Importantly, we do it in a topology-aware way. So the input to Crush isn't just the idea of an object, it's something called the Crush map, which is a structure that Ceph users can define to say, this drive is in this host, is in this rack, is in this chassis, is in this data center, and so on. By default, we create 3 copies of data, and we put each copy on a different host. And we detect which drives are in which hosts by just looking at the host names. So it's a quick calculation. We don't have to do we don't want to be wasting a lot of time recalculating this. And when you want to customize it, there is a simple language that you can use to specify what we call a crush rule. And this is the entire syntax of the language. And it essentially lets you specify a series of steps along the lines of pick one rack. Okay, now pick 2 drives. Okay, now pick another rack. Now pick 1 drive, and so on. As well as specifying where in the topology of your servers and racks and so on you put things, you can also choose to define a crush map that puts things like SSDs and hard drives, or higher performance and lower performance hard drives, into different regions of the map. And you could do interesting things like put the primary copy of a data on an SSD and also put a copy on a spinning disk somewhere else. That's a fairly contrived example, but it's possible. And finally, just to complete your terminology of Ceph, in the previous diagram, those little colored blocks of objects, we don't actually decide on an object-by-object basis where to put things. We could. It would be scalable, but it would not be efficient. So what we do is we divide up the overall object space into so-called placement groups, and we apply the crush algorithm to each placement group. And typically, a system will have a couple of hundred of these per OSD. So they're fairly numerous things. And those are the placement groups are the granularity at which we do data management. So if we have lost some data and we need to re-replicate it, rather than having to worry about finding a million objects, we know which placement group was lost and we re-replicate that. And placement groups form a pool. And so pools are just a logical data management concept within Ceph. So within your Ceph cluster, you say, I would like a pool. The pool will contain some thousands of placement groups, which are, again, simply virtual things, imaginary things. And then objects are assigned by their ID hash into a placement group. And when you want to write the object, you use the crush algorithm to work out where the placement group lives, and that's where you'll find the object. Don't worry if you didn't completely follow that or if I didn't explain it very well. It's not essential to the understanding of the system. It just comes up subsequently if you're looking at Ceph and you think, what are these placement group things? That's what they are. The way that resilience is implemented in Ceph is initially a peer-to-peer heartbeat between the OSDs and the system. So they will constantly be checking if their neighbors are still alive or not. And if they're not, they'll send a message to a monitor server to say, I believe my neighbor is dead. The monitor server will require several of these messages. So if one guy is falsely claiming that all his neighbors are dead, and his neighbors are saying, no, I'm still alive, the monitors will cope with that and realize that his neighbors are not dead. But after maybe 3 or 4 different OSDs have all said, I think this particular guy is dead, the monitors will decide that he is indeed dead. And at that point, they update their state to indicate that he is down, which means that the OSD probably still exists, he's not available right now, and at that point, client workload will start going to the other replicas of that data. So if you had 3 copies of the data, and you lose 1, or 1 goes down, then the other 2 will continue providing normal operations. In the default settings, if you then lose a second copy, then it will go into a read-only mode. Because if you did any writes, then we wouldn't be able to make sure that we'd reliably persisted those writes. Those thresholds are configurable. You can have as many copies as you want, and you can change the rules about how many copies have to be available to service reads. After some period of time, the default is 5 minutes, but you will want to configure this depending on the size and nature of your system. The monitors mark the OSD out. This terminology gets confusing, the up, down, in, out concept. But the distinction is that when something's down, it's simply unavailable to serve data. Whereas when it's out, we need to start making new copies of that data elsewhere. And by default, that happens after 5 minutes. The most exciting thing about this process, other than all the housekeeping stuff, is that when we start making those new copies, it happens on an all-to-all basis across the cluster. If I go back to the diagram with the colors on it, you'll notice that the red block in the top left is next to a blue block, but the red block down here is next to a green block. So that's what, in storage jargon, you call that declustered placement of data. And that means that when we later want to rebuild all the data that used to be on an OSD which is now dead, it's that data that we want is all over the cluster. And we're not having to stream the data from a particular hard drive. So we get much, much better recovery bandwidth than in a RAID system. If you have 4 terabyte drives in a RAID 6 array, I'm sure a lot of you have had the experience of having a drive fail, and it's kind of a nail-biting experience, waiting for a day or two for it to rebuild when you're worried about your degraded system. So beyond simple puts and gets of objects, RAIDOS can do a lot more than you would expect from a typical object store. We can partially update objects. We can store key value dictionaries within a particular object. We can do snapshots of the objects. And we can also use it for messaging. So we have a mechanism called watch notify that allows you to create an object and have some clients subscribe to the object and subsequently have somebody else send notifications via that object. That's the kind of thing that would be very interesting if you had an application built on LibRADOS that needed some sort of queuing or notification. We use it internally for the housekeeping in some of the other layers that we have on top of LibRADOS. And you can also customize it. So in addition to the write, read, and so on transactions that RAIDOS supports by default, you can add code in what's called RAIDOS classes, load it into the OSD, and then call it remotely. So if you have some interesting manipulation that is specific to your application, maybe you want to compress and decompress objects, maybe you want to remotely grep an object on an OSD, you could implement that as a RAIDOS object class. Just a quick note about choosing hardware. I work for a software company, so we don't sell hardware, so we tend to give fairly loose recommendations. But the key idea is that the cost of having these multiple replicas of data should be mitigated by using comparatively cheap hardware. So don't go out and buy a RAID controller. Don't go out and buy a big traditional storage chassis. You want commodity servers with cheap hard drives in. A lot of people even just use SATA drives. And you can get a lot of the performance back that you might lose by using slower drives by using an SSD specifically for the journal on our OSDs. So OSDs do data journaling, which means by default, if you have an XFS hard drive acting as an OSD, every piece of data that you write to it will go on there twice, once in the journal and once on the disk. Clearly, that's undesirable to double your write bandwidth consumption like that. And the way that most people build Ceph clusters is to have an SSD that takes that first write with very low latency, makes it persistent, and allows the rest of the system to continue, gets you a good latency number, and then subsequently flush from that journal onto the spinning disk. And the typical ratio that you use when building a system is to have an SSD with 4 hard drives, something like that. But it's very approximate, and it depends on what hard drives you're using, what SSDs you're using, and so on. That SSD is not mandatory, but it's the typical way people deploy Ceph if they care about latency at all. Make sure you have enough CPU and RAM. Ceph will use a lot more CPU and RAM than a traditional, for example, filer application, because when it's doing things like re-replicating data, there's just a lot more going on. And I'll come on later to the Erasure Coding feature of Ceph, and that requires a lot more CPU as well. And finally, think about the ratios in your system. Think about the ratio of reads to writes. Think about the ratio of storage capacity to bandwidth accessing that storage. So do you need more smaller drives or fewer bigger drives? Do you need relatively little disk bandwidth and a lot of RAM for caching reads? Or are you doing streaming writes and you don't care about reads at all? And that's just different for every system, so take that into account. So I mentioned the 3 different ways of accessing Ceph. I'll talk about those in a little bit more detail now. RBD, the RAIDOS block device, gives you a virtual disk. This is essentially a software SAN. We don't generally call it that, but that's where it would fit into the traditional storage landscape. So in RBD, we take these disk images that we expose to clients, which might appear as /dev/RBD, whatever. It looks just like a drive. But under the hood, each byte extent within that image, within some configurable chunking, by default 4 megabytes, is a separate RAIDOS object. And that's going to get written to a different OSD out there in the RAIDOS system. What that means is you can get really phenomenally good bandwidth. If you're sending a lot of writes to one of these images and you've got a large number of OSDs, then you're really limited only by the network bandwidth from the client. So it's pretty fast. It's fairly feature-rich. Snapshots are very useful. Snapshots themselves, relatively obvious feature, but on top of snapshots, we have an import-export feature which lets you take diffs of a disk image. And that's very useful if you have multiple data centers and you want to keep a asynchronous backup of some of your images. You can use snapshots and the diffs, it's called RBD import and RBD export, to implement that. And a lot of people have very simple scripts that do that. It's also more or less a default part of typical open source virtualization stacks. So it's in OpenStack, it's in CloudStack, it's in OpenNebula, it's in Proxmox. The chances are whoever you're using for your open source virtualization has already heard of RBD. And that's just a visual representation of that. So the virtual machine is sitting on top of a disk, is sitting on top of, well, is being managed by a hypervisor, and then that write or read workload is getting spread out across the Rados cluster. Next up, Rados Gateway. So this is, from an applications point of view, the simplest one. It's providing a relatively straightforward S3 compatible API. Until recently, it was most of the S3 API. We're more complete than we used to be. We have versioning now. And it has all of the accounting type management and the user management permissions and so on that you'd need for a system like that. And the way that Rados Gateway works is to have a series of web servers sitting in front of your Rados cluster. So you can have as many of these as you want, and they coordinate with each other to make sure that they're not treading on the same objects at the same time. And they do that using the aforementioned Rados watch notify mechanism, so they do it scalably. And so you have a separate cluster of Rados Gateway web servers acting as a front end to your underlying Rados cluster, which is doing all the storage. And those web servers themselves aren't storing anything. They're more or less stateless. So they can come and go. You don't have to worry too much about the reliability of those. Finally, CephFS, the file system. Right. So CephFS, you can mount it on a client machine. The client software for CephFS is actually part of the mainline Linux kernel, so the chances are you already have the CephFS client. And once you've mounted it in /mint/ceph or wherever, it looks just like a normal file system, and it has the same POSIX semantics that a local file system would have. The trick is that it sends its data directly to Rados. So in the same way that an RBD image can stripe its data across all of those OSDs and get very good bandwidth, you get the same capability with CephFS. In order to provide POSIX semantics, we introduce an additional service, the Metadata Server, or MDS. But it's important to just clarify, the data does not all flow via that, and the object lookups don't flow via that. The Metadata Server is purely for the POSIX file system metadata. So for example, the inode, the directory entry, the directory, and so on. Once you've got a file open, all of your writes from the client go straight to the underlying Rados layer, and you get the same fabulous bandwidth and so on. And that's what that looks like. The clients are talking to metadata servers and data servers, and in that cluster at the bottom there, in addition to the M's and the OSDs, you see the MDSs in there as well. They're managed by the monitor servers as well. So in the same way that the monitors keep track of which OSDs are up and down, they do that for the MDSs as well. CephFS actually goes a little bit beyond what a typical POSIX file system can do. So we have subdirectory snapshots. You can take a snapshot of a particular directory. You get recursive statistics. So if you want to know how much data is in a particular folder, by default, if you use DU on a Linux system, it's actually going down into all of the files in there and touching all of them to calculate that. In CephFS, we keep that data to hand. So if you have the right user space tools, it will be able to look that data up directly. And that's especially important in a distributed file system, because if you've ever used something like Lustre with a big directory and you type ls-l, quite often you'll find it actually takes a while because it has to go and talk to a lot of different places in the system to get all that metadata together. So recursive statistics can really speed that up. And this is not so much a POSIX file system feature, but it's something that's quite important to mention. You can have multiple metadata servers. So we get away from that bottlenecking issue that some systems have. CephFS is not part of the officially supported products that most of the enterprise vendors providing Ceph distributions are providing at the moment. The reason for that is that the recovery tools aren't done yet. So the file system check and the ability to repair systems after something's gone wrong aren't there yet. So the system, the file system works, but on the off chance that you hit a bug or you have a data corruption issue or something like that, you have quite a difficult time at the moment. So that's the priority that those of us working on CephFS, myself included, are working on getting those recovery tools and those consistency checks online so that people can make use of CephFS for more production-sensitive workloads. And all of that complexity aside, if you already have a Rados cluster and you're using our Ceph deploy tool to set up your system, setting up CephFS is actually incredibly simple. You create an MDS using Ceph deploy, you create a couple of Rados pools, one for your metadata and one for your data, and then you ask it to create you a new FS, and finally you mount it on a client. And like I said, the chances are your client machine already has the software on it. So I've covered Rados, the underlying mechanism that we use to provide the storage and the resilience. I've covered the different interfaces that you have to Rados for your applications. I'm going to go on and talk about some other slightly more advanced topics, but before I do, I just wanted to ask if there are any questions about what I've covered so far about terminology and that kind of thing. Okay. Yes. So the question is, what about access control lists in CephFS? Yeah, that's an area that needs some work. So different systems, different platforms, whether you're using NFS or Samba and so on, have different requirements in that area. And a related thing is support for SE Linux and that kind of thing. So we have extended attributes in CephFS, and we have the whole standard Unix permissions mechanism in CephFS. But in terms of the specific ACL capability for specific platforms, there is some work needed. Okay, so that's a great question. I should clarify that. The question is, can I mount CephFS from multiple clients at once? And the answer is yes. That's the sort of technical definition of shared in the context of file systems. So in file system jargon, a local file system would be something like ext4, and you could have a remotely accessed ext4 file system if you had iSCSI in the middle or something like that, whereas a shared file system is something where multiple clients can mount it at the same time and do operations in it at the same time, and they will be consistent. So having two processes running on separate hosts using two different mounts has the same POSIX consistency guarantees as having two processes running on one machine looking at the same mount. Somehow, somewhere in locker.cc, yes. Yes, at the back. Okay, so the question is, what about small files in CephFS? You're right, it's an Achilles heel of distributed file systems, generally. Small file support in things like, Lustre and Gluster, the established players in this area, in the open source area. To a certain extent, it's inevitable that you pay a latency cost for each metadata operation that you do, and you hopefully amortize that with some bandwidth afterwards. And in small files, that equation's working against you. So in CephFS, there are a couple of things that we do. One is that the clients cache a lot of metadata, and that includes a fair bit of intelligence about whether they have a complete directory or not. So in many cases, when creating files, we don't have to do a round trip to the MDS each time. A client can know, I created this directory, I have a complete picture of it in my cache, and so I can go ahead and create a file without having to ask the MDS for permission. The other thing we do is inlining. So for very small files, and this is an optional feature that you can enable because it's not a good thing for all workloads, you can say the file is below a certain size, and so instead of sending it to its own Rados object out there in the cluster, I will send it with my metadata operation to the MDS, and the MDS will store it along with the inode in the same place the MDS stores it. So in that instance, you have a lot fewer objects in your Rados cluster as a result, but it's a compromise. You're sending more data via your MDS at that point. So there's no silver bullet for small files in a distributed system, but we do have a couple mechanisms in place for dealing with that. So I'm not a Gluster expert, so the question is, do we have something equivalent to a feature where Gluster uses a local volume for caching? I mean, we could take that offline and talk about exactly what that is in Gluster, because I'm not familiar with it. But in general, there are some tricks that you might do in a system like Gluster where you have the files stored directly inside a brick that wouldn't necessarily apply to Ceph, where files are translated into objects that are stored across a whole cluster. So I would doubt there would be a one-to-one mapping of that method, but we can talk about it if you like. Okay. So I want to introduce not just the basic default settings for Ceph, but a little bit of the extra stuff that it can do. Some of this stuff it hasn't been capable of doing since before relatively recent releases. So this is comparatively new stuff. Erasure coding and cache tiering was part of the Firefly release of Ceph that came out in spring of last year, so a little under a year ago, which in sort of enterprise software terms is incredibly recent. But we're doing like two stable releases a year, so that's already 2 releases old for us. So firstly, cache tiering. This allows you to take two Ceph pools, 2 Rados pools. I almost said Ceph FS there, I'm obsessed with it. And use one as a cache to the other. So the reason you would want to do that is that you can use crush rules to place a particular pool onto particular storage. That means you can have an SSD pool and a hard drive pool, and use the SSD pool as a cache to the hard drive pool. That's pretty useful if you have the right kind of data set for it. If all of your data is comparatively hot data, then this won't do very much for you, because you'll constantly be thrashing your cache. But if you have a fair bit of warm to cold data, like old versions of disk images, for example, or old snapshots of disk images, then you can use this to make sure those end up getting migrated down to spinning disks, while all the stuff that you're accessing day to day might remain on your SSD tier. So the kind of caveat with this is that cache is a persistent cache that's doing synchronous I/O. So it's a normal Ceph pool, more or less. It is giving you the same kind of resilience guarantees as you get with any other Ceph pool. And that means that operations like promoting something to the cache from your backing pool are comparatively expensive, because you have to write this resilient, redundant copy of your data into the cache. I mention that not to discourage you from using cache tiering. It's an incredibly useful and powerful feature, but just to clarify that it's not a catch-all. It's not something you want to enable on all systems, because it depends on your workload and it has those caveats. The feature that goes best hand in hand with cache tiering is erasure coding. So erasure coding is a piece of jargon which essentially means RAID 6 or RAID 5. So this is where you take a piece of data and you break it up into M data chunks and K parity chunks. So for example, if you have a 10-disk RAID 6 array, then you'd have M equals 8 and K equals 2. So Erasure Coding in Ceph takes that model and applies it across the RAIDOS cluster. Instead of having 3 copies of one piece of data, we break the data up into M plus K chunks, and we scatter those across the cluster. The important thing about Erasure Coding is that it gives you much more efficient use of your underlying storage than replication. So if you do 3-way replication, that's a 200% overhead in terms of disks, which you can make financially. You can make a certain amount of that back by the fact that you didn't have to buy expensive disks or RAID controllers to begin with, but it still kind of hurts for some workloads if you've got really large amounts of bulk data. So Erasure Coding is the solution to that within Ceph, that you can use Erasure Coding for those workloads that have large amounts of bulk data that you don't necessarily access that often, but you'd still use replication for your day-to-day nearline data. Erasure Coding isn't just a little more expensive to do than replication. I mean, I don't think I actually called that out. So Erasure Coding is a calculation. It's mathematics. It has a CPU load associated with it. And you're also breaking the data up into more chunks. You're talking to more different OSDs. And in a distributed system, you have a weakest link latency effect. So your latency of an operation will be the latency of whichever OSD responded slowest. So statistically, if you're writing to more OSDs, your latency tends to get a little bit worse. You will also find that what you can do with an erasure-coded pool in Ceph is a little bit more limited than what you can do with a replicated pool. Your RAID controller in your traditional server will let you modify the data however you want. It'll let you go to an arbitrary byte and write a 1 instead of a 0. But under the hood, the reason RAID controllers are comparatively expensive specialized pieces of silicon is that what it's having to do that is to read that block back, modify it, chunk it up again, encode it again, and write it back to disks. Which is why when you're doing high-performance applications with an enterprise RAID controller, you are frequently advised to do things like 4 megabyte aligned writes. It's because of this. So in Ceph, rather than just letting you do that and having you take the hit if you're unwary, we restrict what you can do with an erasure-coded pool. We don't let you modify things within it. The way we make that into a usable system is to combine cache tiering and erasure coding. So you can put a replicated pool that we'll use as a cache on top of an erasure-coded pool. So you're paying a 200% overhead in terms of storage space in your replicated pool, but you're going to get really nice, consistent latency numbers, and you're going to be able to do everything with it that you could do with any other pool. So you can run RGW, RBD, CephFS on top of that pool. And then any data which doesn't get touched for a long time gets migrated transparently within Ceph to the cold pool. And there are configurable cache settings here for how many objects you want in your hot tier and how long things have to be there before they can get migrated and so on. But for a lot of workloads, that gives you a really great balance of efficiency of use of storage and flexibility and speed for the stuff that you access often. And this can all coexist with any other stuff you have on your Ceph cluster. So you don't have to decide up front, my whole Ceph cluster is going to be like this. This is a pool-by-pool thing. And you can have pools addressing different bits of physical hardware, so you have a lot of flexibility, and there are a lot of different ways to wire this stuff together. But this is a typical one. And just to give you an idea of what the administrative overhead is of setting something like this up, well, this is a few commands more than it took to set up a Sef file system. But it's still fairly simple. For something that powerful under the hood, we're creating an erasure code profile where we're setting our K and M. So unlike a lot of legacy RAID controllers, this is completely customizable. You can pick your ratio. Some ratios are more efficient than others based on the underlying mathematics that's going on. But you can do things like having, M equals 10 and K equals 2, or M equals 10 and K equals 10, and get to a position where you can tolerate a very large number of losses before you would have lost data at the cost of more storage space and at the cost of having to do more mathematics when you write something. And then similarly to what we did with CephFS, we create a pool for the cold tier, we create a pool for the cache tier, and we use a few more commands to associate them with each other. And from that point onwards, any application that accessed the tier that I called cache would be entirely unaware that there was also a cold erasure-coded pool sitting beneath it. So you have a total abstraction beneath the cache tier in that case. Finally, I want to talk about what's new. So Ceph 0.94 came out, I think, last week, very recently. It's called Hammer. So we have an alphabetical naming system where we're picking the names of different cephalopods and squids and octopuses and so on. So the next one after that is Infernalis, which I think is a great name for a piece of software. It sounds very heavy metal, I think. So in Hammer, I'm just going to run through what's new in each component. So in the underlying Rados layer, the main new thing is performance. So we've had a lot of great contributions from companies like SanDisk, who are interested in running Ceph on their high-end solid state and, in some other cases, non-volatile memory storage. So they're interested in IOPS. That's involved a lot of re-architecting of bits of the software. So there are parts of Ceph that were designed around the idea of spinning disks, where you had a lot of latency from the disk to play with. You didn't have to worry too much about your latency in software. But that latency matters a lot more when you're trying to send hundreds of thousands of IOPS to a single PCI Express flash device. There is a new crush setting in Hammer called Straw 2. You don't need to worry too much about that, but that's an incremental improvement on some corner cases where you are adding or removing disks, and you might have been doing more data migration than was otherwise necessary. And cache tiering has a new setting that will allow you to do reads straight through into the erasure-coded tier without having to promote things to the cache tier. So for some workloads where you just periodically need to do a single write of something without taking that hit of promoting it, you can get much better performance now than you could before. RBD has had efficiency improvements as well. So we maintain a map now of which parts of an image have ever been written to, so that when we do things like exporting and importing and cloning, we can do a much more efficient version of that. There is new locking in RBD if you have multiple servers that try and access the same RBD image. That is rarely what you actually wanted to happen. If two servers try and mount the same ext4 file system on a shared block device, bad things tend to happen. So that's safer than it used to be. In Rados Gateway, we have new support for the S3 object versioning API. So that's a neat feature that Amazon have in their S3 implementation that lets you implicitly create new versions of objects every time somebody writes. It essentially makes your S3 bucket version controlled. So we support that now. And there's also been another efficiency improvement in RGW that previously there were some scalability limits on how many objects you could have in a single bucket before things started slowing down. And that's been removed by sharding up some of our metadata across multiple objects. Finally, and closest to my heart, CephFS, the Sef File System, has seen a lot of work over the time between Firefly, which was the previous long-term supported release, and Hammer. So mainly, this is about resilience, it's about hardening, and it's also about usability. So people who have used distributed file systems before might have come across the cases where something goes wrong. Maybe there's a server not responding, or something's gone wrong internally. And the way you find out about it all too often is that you go into a directory and type ls, and it just sits there because it can't service that request, or it's waiting for something to happen. So we've added a bunch of health checks and diagnostics to CephFS so that it will now be able to proactively tell the administrator that, oh, this client isn't responding to an RPC that I sent it, or this client has a behavior which indicates you've hit bug 768, you might want to restart that guy, that kind of thing. We've also added some recovery tools. This is a work in progress. So the metadata servers in CephFS have a journal as well as their main store for the metadata. And where we are at the moment is that we have a bunch of the tools for checking and recovering journals if something goes wrong. That's in Hammer. And at the moment, we're working on the recovery tools for the other stuff, which will make it into a subsequent Ceph release. There's a new online scrub for the metadata. So checking that if we have an inode in our metadata pool, that the corresponding data exists and has the size we think it did in the data pool and that kind of thing. That's the kind of thing that a file system check might do in a legacy file system, in a local file system. But we have to do that online because the size of these systems, we're talking about multi-petabyte systems, doing that offline means taking your system offline for an unacceptably long period of time. A little bit of housekeeping stuff. So filling up a Ceph file system used to be kind of an interesting experience in terms of how it would respond to that. It has safer handling for that now, and that's mirrored in an increase in the amount of QA we've done with Ceph as well. So there are a lot more tests for Ceph now. It's in the progress of being stabilized. And there's also new support for client quotas. So Ceph has a kernel client. It also has a Fuse client. These quotas are currently only supported in the Fuse client, and they're not completely strict. A client can slightly overrun its quota, but that could be useful if you have a use case where you've got multiple users and you want a general sense that they're not going to be able to have too much data. Finally, here are some links for you to get involved. Come to the mailing list, come to the IRC channel. Like I said, like everything else at this conference, it's completely open source. So we rely on you. We rely on your feedback. We rely on your testing. Try not to swear too much when you're giving us the feedback, but if something's broken, we'd like to know. And next Tuesday here in Berlin is the next Ceph Day Berlin. So if you're free next Tuesday, go to that link, and there are still tickets available, I think. So I'll turn it over to questions now. Thanks very much. Yes? I'm sorry, I didn't catch that. So the question is there a roadmap for Ceph? No. That doesn't mean we're not doing it. What it means is that we're not saying it will be done by this date. The main sort of marker in the road for us is having those recovery tools in place. So it's less about claiming that there will be 0 bugs, because all software has bugs. And Ceph already, for the last couple of years, hasn't had a serious data loss bug anyway. It's more about getting to a position where if there was a bug, hypothetically, that damaged someone's data, we would be able to recover from that without having to send one of our developers on site to manually hex edit things, back into the right state. So, but that's our kind of goal, and that's something that's being worked on right now. Yes? Mm-hmm. Right. So the question is, does the OSD do checksumming? And you're quite correct. That's left either to the underlying application, the underlying disk, or to the application. What the OSDs do is scrub. So if there are 3 OSDs with a copy of a particular piece of data, then they will periodically compare notes about that data. So we have 2 types of scrub. There's scrub and there's deep scrub. And the default scrub, which happens, I think, daily by default, is a metadata check that they agree about the version of things and that they have the same number of objects in a placement group and that kind of thing. And then the deep scrub is where each OSD holding a replica of a placement group will go down to the disk and read every single byte and calculate a checksum on the fly, and then compare those checksums. So we don't do checksumming on the fly, but we do periodically scrub the data. And if you have 3 copies and one of them disagrees with the other 2, then we can recover from that. Mm-hmm. So the question is, if you change the crush algorithm to straw2 after installing Hammer, can you do a live migration of that? So you can, you don't necessarily want to. If you change the algorithm in use, that will change the calculated locations for the data. which will result in movement. So most people on live running production systems don't choose to take that hit, because obviously it generates a whole load of I/O workload on your system. And if your system is running happily with an existing algorithm, then it's not really worthwhile to move to the new one. Mm-hmm. Not quite. So you can apply this algorithm on a pool-by-pool basis. So if you had some new OSDs and you decided that the data you put on those OSDs you would put in a different pool, then you could choose to use that algorithm within that pool. But you can't apply the algorithm on a per object basis or a per disk basis. It's a per pool thing. Okay.
Okay. Any questions? Come on, one more.
It's yeah. So the question is it standard to have 3 copies of the data? It's the default. It's completely customizable. In general, I mean, I've seen people using 2, I've seen people using 4, but I think most people are using 3. It's kind of accepted as a reasonable trade-off for replicated systems. 2 is pretty risky. Double disk failures on a large system are not rare. It will tell you, and then it will be your problem. Yes? Mm-hmm. Yep. The question is, how do you monitor Ceph and get metrics out of it? So you have a choice of tools. What Ceph comes with by default is just command line tools. So there is a Ceph status command that will give you an overview of your system. And there are also, each daemon in the system has what we call an admin socket that you can send commands to ask it for things like performance counters. On top of that, there is a Diamond plugin. So Diamond is a Python package that will send statistics to Graphite. Diamond has a Ceph module, and that knows how to talk to our services and take the statistics and send them home. However, there are a lot of statistics, so make sure you have a good Graphite server before you try switching that on. Finally, there is Calamari, which is a monitoring and management web application that's I think there should be a new version coming out soon. So far, the packaging of that has been a little challenging because it has a lot of dependencies. But if you go to our website, it's on there, and there's a Ceph Calamari mailing list for that as well. So you have a number of different, and there are also a couple of other third-party GUI web apps that other people have written. That I can't remember the name of any of them at the moment, but yeah, you have a choice. Yep. So the question is, would it be sensible to run something like Graphite or MySQL on top of Ceph for those type of workloads? Yes, you can. Yes, people do. You will never get the same latency out of a network system that you get out of a local system. So it depends. I mean, it sounds like a get out all the time, but it really depends on the workload. Graphite's actually a really interesting example. I don't know anyone running Graphite on top of RBD at the moment, but I have looked at the I/O patterns that come out of Graphite, and it's an example of an application that will pile I/Os into your page cache and then gradually drain them out the page cache onto disk. And I would expect that would actually probably work pretty well on Ceph if you tried it. But if you need the latency of a local SSD for your database, you need a local SSD, and no network system will ever give you the same performance. But yeah, I mean so not all SANs are created equal, and not all Ceph clusters are created equal. So the performance you get out of your Ceph cluster is going to depend what hardware you buy. So if you buy some nice fast low latency 10 gig NICs, and you put all your data on SSDs and you have nice fast CPUs, then you will get pretty good performance. Whether it will be faster or not than an uncontended SAN over Fiber Channel, my money would be on the SAN, but the Ceph cluster would probably be better value for money. Oh, absolutely, yeah. The caveats around CephFS do not apply in any way to the rest of Ceph. So RBD and RGW are entirely ready for production, yes, yeah. There's actually a really good case study that just came out last week. If you want to Google for it, Yahoo published a developer blog about how they're using Ceph for their internal data storage. So they're using Rados Gateway along with Erasure coded pools. And they have a number of Ceph clusters that they're using as pods. I think each pod is 3 petabytes, something like that. So it's a really nice case study of Ceph being used at scale.
Okay, any questions? Then one more question from my side. Is it possible to control the load executed by deep scrubbing? So a deep scrub is running, my USD is under load, and the next write is very slow.
Right. Yeah. So I think this made it into Hammer. There is some I/O prioritization that would deprioritize deep scrubs compared with client I/O. There are also some patches for more intelligent scheduling of deep scrubs. So traditionally, it was if you haven't been deep scrubbed for a week, then deep scrub, which meant a week after installing your cluster, everything would decide it needed to deep scrub. So it's a bit smarter than that now. But even in that case, it's not as bad as it sounds, because there's also a per OSD setting of how many PGs it will scrub at one time, which by default I think is 1 deep scrub at a time, something like that. So it is already somewhat configurable, but it will become more configurable as well, because that has been a pain point for some configurations. Yes, in the back. Okay, so the question is there a way to warm up a cache tier before I send my client traffic to it? There are explicit commands for demoting and flushing things from cache tiers. I'm not sure if there's an explicit way of promoting things in advance either, but ordinarily the way the data was written to begin with would have been via the cache tier. So the way you put the data in your Erasure coded pool to begin with was via the cache. So it would already be in the cache unless it had fallen out. Okay, so all right, so you're adding a cache pool to an existing backing pool. I would have to get back to you on that. Yes. Yes. The rules get a little bit more complicated. So you can have write-back cache tiers. You can also have read-only cache tiers. You can definitely have multiple read-only cache tiers for a single backing pool. So that's a kind of natural use case if you wanted a cache tier in each data center or something like that. Having multiple write-back cache tiers probably doesn't make sense from a consistency point of view, because in order to maintain consistency, each cache pool would have to be talking to the other ones, and we don't do that. So yes, you can have multiple cache tiers, but having multiple write-back caches on a single backing pool may not in general make sense unless you have a workload that's tolerant of inconsistency.
Okay, the time is over now. Thank you very much.
Thank you.